Swayam Prabha. Digital India. Educated India.
The next presentation is coming from the Baroa Institute of Technology. The presenter will be Bandura Kiran.
Yes.
Okay, so the title of his talk today is Techno-Economic Feasibility of Energy Integrated Bioethanol Production from Various Feedstocks. So please start.
Thank you, Professor. Thank you very much for the PSC to give the chance to me present my work here. Basically, this work is done by my undergraduate student. So my today's talk is on techno-economic feasibility of energy integrated bioethanol production using various feedstock. Coming to that introduction part, you know that the bioethanol, why we are, many of the governments are looking for the bioethanol production is that, so to save the money on the foreign, that like you can say that the foreign currency we have to spend on that to import the crude. To reduce to save the money, the Indian government also like started that they started the plan to implement the 20% blend with the gasoline to reduce the near about $30,000 of foreign currency. And you know that bioethanol can be produced from the various feedstock, that is I can say the sustainable sources like starch and biomass and woody type biomass also can be used to generate the bioethanol. And not only that, we can use that ethanol as a fuel, you can use as a like many side products also generate from this ethanol. One is the major thing is that pharmaceutical industry, and also another one is that cosmetic industries. That these are the three industries majorly use the bioethanol as a one of that feedstock. And our students formulated their objectives to for their capstone work. They are done under my guidance that. So they formulated these objectives. One is that to develop the models in the Aspen place for the various feedstock for the production of bioethanol. And they done the study of that comparison study for the yield percentage in the both feedstock. And also we try to improve the energy performance of that the process. So they introduced the heat integration technique in that to say that it will be more environmentally, like you can say the more energy efficiency of the process will be enhanced when compared to the conventional process. And the final one is that the economical study, that is the main thing to finalize any process. Without this, we cannot be confirmed with that our study is whether feasible or not. And basically our study, that in simulation study, we divide into that 5 part. One is that dilution part, that it comes under the free treatment. And the second one is a liquefaction, that is nothing but you can say that phase transition, that is from the solid, mostly our feed is a solid content only. So that we convert into that liquefied form. And the third one is a saccharization, that is nothing but it's a conversion of the liquid starch into that fermentable sugars. So, and the fourth step is the fermentation, is the main step in that to convert that organic matter into the fuel. And here the ethanol will be produced here in the fermentation step. And the final is a distillation, nothing but it's a separation. So there, you know that bioethanol and water, we can't be separate easily. It forms that isotope. So there is various ways to separate the bioethanol. One is that isotopic distillation. Another way is to pressure swing distillation is another method to separate the bioethanol and water. And in our study, we consider only that extract to distillation by introducing the solvent, that ethynyl glycol. And this is the block flow diagram of that one of the feedstock, that is starch feed process. Here in this, first step is that pre-treatment step. Here, feed it considers the solid that and the first step is that liquefaction. Here, the phase transition will occur. The solid feed will convert into that liquefied form of starch, and then we have to be sent to the feed aggregation reactor. There it will be convert that liquid starch into that fermentable sugars. And then we need to be add that enzyme to convert that fermentable sugars into that bioethanol that is in the fermenter. And the final last step is the separator here. As you know that it's not only single product will form, it along with the ethanol, it form the water and some other byproducts also form. That has to be separate to get the main product as a ethanol. Here main product is ethanol. Along with that, the solvent which you are using here, that ethylene glycol, that also be record, and so that record ethylene glycol is used as a and next cycle of operation is used as a recycled product. Okay. So this is one of the feedstock process, that is a starch feed process, and mainly the reactions are to develop the models of the reactors. We use that conversion base mostly. That our main objective is to improve that how the process can be enhanced that in terms of energy as well as economic wise. We look into that way only. That's why we simulated that in the based on the conversion base. The first step liquefaction, mostly it's convert the starch into the dextrine 100%. And the second step is that feed saccharization step, that the dextrine and water will be converted into the glucose, that is a fermentable sugars. And the third one is a fermentation. So these three reactions will be involved, occurred in the fermenter. And finally that here will get that ethanol, some of the other byproducts are glycerol, and water will be formed here. So then the second process is that second feedstock process is that cellulose feedstock process. Mostly will be like you can use that wheat meal, woody biomass. So this type of things can be considered as a cellulose feed. It contains the cellulose. In this method, in this process, we have to use a pre-treatment step to remove that lignin present in that. Why? Because it will be inhibit that fermentation process. To avoid that, we need to be remove the lignin from that. So that's the main in the pre-treatment step. And third step is that fermentation. The fermentation is common in that things which we discussed in the starch process, starch-based process, same way. And the final is a separator here. 3 distillation column will use here. So why is one is separate that bottom product that will mostly will comes under the glycerol. And the second one is the distillation here will separate the ethanol. And the third one is recycle. You can see that ethylene glycol and water. So these are the reactions involved in the feed treatment method. These are the reactions will be involved in the pre-treatment method. And these are the reactions will be involved in the fermenter. And these are the feed intake, feed composition we consider for our simulation study that. So these are the models. This is the model is developed for the starch feed in Aspen Plus. So you can look here, 3 reactors are there. This one is a liquefaction reactor, this one is a feed saccharization reactor, and this one is a fermenter reactor. After reaction that, it has to be go for that separation step. Okay, so this is the conventional method of separating that, producing the bioethanol from the starch feedstock. So this is the second method, this is the model for the cellulose feed. Here also will involve the 3 separation unit. Okay. And here only two reactors will be involved. One is the pre-treatment method and the fermenter method. And the rest of things are same, like, but in compared to that cellulose feed, we'll have the many byproducts compared to the starch-based feed. And we done the sensitivity analysis to finalize that number of stages. These are the common method to fix the number of stages, feed fed location, and reflux ratio. Based upon that separation efficiency, we'll decide the number of stages and feed fed location, and the reflux ratio will be decided based upon the separation efficiency as well as in the reboilerability. And the same study is the conducted for both the cellulose feed also. And third one is that economic analysis for the both that starch feed as well as cellulose feed. We have done that economic analysis by the help of Aspen economic analyzer. So we consider that 8,200 operating hours for the evaluation of that capital cost and the operating cost evaluation for the both the process. So these are the main indicators for the start speed. That one is that capital cost is around 77 lakh 88,030 rupees, 30 USD, and the operating cost for a year is 23 lakh 2 lakh 30,000. Sorry, 23 lakh 7,800, and the total utilities cost for a year is around 5 lakh 89,106, and equipment cost, and each component wise we given. And in the coming to that payback period estimation, the start speed will give that less feedback compared to payback period compared to that the cellulose base feed. That's around 3.5 something you got. So coming to that economic analysis for the cellulose feed, so we use that same Aspen economic analyzer to perform that economic analysis. So these are the main indicators. If you compare with that start speed, it has the payback period around 3.3, around 8 months is more than that cellulose start speed. Coming to that energy integration, that why we want to go for the energy integration, that like in both the process, near about 3 distillation columns are used. So you know that distillation is that energy intensive process. To improve the energy performance, we can go with that different heat integration technique. Basically, heat integration techniques are divided into the 2 categories. One is the internal heat integration, and another one is the external heat integration. So mostly the external heat integration won't create any issue. That why? Because it won't affect the internal of the distillation process. But internal heat integration, so it will be impact that internals of the hydraulics of that. You can say the liquid and the vapor rates will be disturbed because of the internal heat integration. So here in this study we consider that internal heat integration. Why? Because external heat integration is only be feasible for the when you are working under closed boiling point mixture separation. And if you are dealing with the wide boiling point mixture separation, that won't be economically feasible. Why? Because the compressor operating cost will be very high in that wide boiling point mixture separation. So for in this study we consider only internal heat integration, and that is intermediate heat integration through that vapor recompression. So here in this process, the overhead vapor will be, some part of the overhead vapor will be compressed, and then because of that compression, that the boiling point elevation will occur. That will be used for to heat it up the reboiler stream. So by this way that it can reduce the load on the reboiler as well as condenser. So why? Because that vapor we are not sending to that condenser, the amount of the vapor which we are not sending for the condense to condense. And in case of the reboiler, the same, the liquid which are producing at the bottom tray is that amount we are not sending for to reboiler to generate the boil up. That boil up will be generated with the help of the heating, the overhead stream is heating that to generate the boil up. So this is the phenomena. And why we use the internal heat integration is that it's a wide boiling point mixture separation. As we know that it won't be economically feasible if you're going with the external heat integration. Another thing is that we can go for the internal heat integration with dividing that distillation column into 2 different sections. That way also we install multiple heat exchanger to exchange the heat between the stages from the low pressure column to the high pressure column. So to avoid that disturbance in that, we only gone through that intermediate heat integration, and that too intermediate heat integration, which stage we have to be connect, that also we perform the sensitivity analysis to finalize the based upon that energy consumption and the compressor load. So, and finally that how we will be calculate the total energy consumption for this study is that Q reboiler plus 3 times of Q compressor. So why we include the 3 times? Why? Because we are using the compressor, right? The compressor directly won't work. So it has to motor we need to use to run the compressor. And how we will get the, mostly we'll use that electricity only. That to generate the electricity we need to get it from the coal, mostly will from the coal. So it will involve the 3 processes to convert into to run the compressor. That's why we consider the 3 times of energy when you go for the total energy consumption. So when you look into the total energy consumption of this column, so what is the reboiler duty required for to run this column plus 3 times of compressor duty. That will give the energy consumption for this system. So this is the way to calculate the energy efficiency. We already calculated what is the energy consumption for the conventional method. We compare with that what is the energy consumption in the conventional method minus that the vapor recompression method. So that will give the around, with only we done for the single column, that it gives around 13% of energy savings. If you same technique will be incorporated in all the 3 columns, so it can be go up to around 40% of energy savings. So with including the that VRC vapor recompression, so this is the cost. Only the extra cost is that installation, that compressor cost is we have to be included along with the conventional method. Coming to that conclusion, that in way to that yield-wise comparison, that around 570 kg per hour of starch is producing that starch-based process producing the 575 kg per hour of ethanol. In case of cellular lignosulfate-based material, it gives only 183 kg per hour. And both the methods are getting a separation efficiency of bioethanol around 99%, around 99.86. And the payback period for that starch-based process is around 2.5 years. For the cellulose-based process, around 3.3 years. In terms of the energy consumption, so it will, with the single column, we done that internal heat integration. That gives around 13% energy savings. And if you incorporate the same study for all 3 distillation column, then it can go up to around 40% of energy savings. So that's all. Thank you.
Thank you very much. So,
Hi, Anwar here from Institute of Engineers Malaysia. Just want to understand about the compatibility of the various feedstock. So I believe that from the topic itself, it seems like we're going to have a same plant or processing facility to have all these various feedstock. So I just want to understand about the compatibility. I mean, of course, since we have a different feedstock, then we'll be having a concern on this compatibility. So I appreciate if you can explain further on that. Second question is that on the, if you refer to your block diagram, you are introducing some sort of alcohol also into the distillation column. So I'm just wondering, why are we introducing some other properties, some other component in the distillation column, whereby we need a distillation column just to distill the product that we are looking for. And the last one is basically on the energy integration, where you have all these compressors, heat exchangers. So I'm just a bit confused because you are getting the source to the compressor, the same outlet that coming out from the condenser. So I believe those are the ethanol, am I right? So this ethanol is, so I'm just curious, why are you considering this ethanol to be sent to the compressor? So we need gas in order to compress further and try to recover. So on top of that, how are you actually gauging in terms of practicality that you can recover the energy? Because you are introducing the compressor, which may need really huge amount of energy, relative to recover whatever heat or to minimize the reboiler duty down there. Thank you.
Yeah, nice question. So one thing that first question answer is that both the feedstock won't carry the same method of pre-treatment. So that's why we have to go with a different process. Okay, and the second is related to that why you introduce that ethylene glycol, right? It's a solvent. Why? Because ethanol and water will form the isotope. We cannot get the more than 79% of purity. So we have to break the isotopes. For that, we need to use the solvent that we are using here, ethylene glycol. And the third one is that the VRC, we are using only for extracting the latent heat from the stream. We are not disturbing the stream. That the vapor which you are generating on the top of that column, that we are simply exchanging the latent heat to generate the boil up. By this way, you can reduce that energy dependence on that reboiler.
Okay. If we are using the condensate or the cooling water from the condenser, so I'm just, because normal practice is that, or normal application, we are not really seeing the cooling water that being coming out from the condenser as a vapor condition. So there is a reason I'm curious there.
Yeah, that we are using the condenser cooling water, right? And the heat which you are extracting from the stream, you are not using that. We are sending that water to cooling tower to regenerate that process stream. So the heat which you are wasting to that cooling water, so that can be recovered with the help of this technique. Hope it's clear.
Hi, what was the price of ethanol that you assumed for calculating the payback period?
Here we are not include that stream product cost and that raw material cost, only that processing cost.
Yeah, but in order to get the payback period, you will need to assume certain product cost. What is your revenue?
In this study, like we are not include that raw material and the product cost. You know that product will be the high cost compared to that raw material, but
Okay.
you only did the processing cost.
Okay, okay. And just one more comment, if I
Yeah.
can. I'm a bit surprised that your capital cost for cellulosic process is lower than that starch. I think you should probably check that.
Mainly because of that, the two section of operation it has to be undergo cellulose compared to that starch-based process. Starch is more than 2.
Okay, thank you.
That may be that.
Okay, so now I think it's time to close this session. So thank you very much for coming and attending this session. And I'd like to thank all of the speakers and audience. Thank you very much.
Thank you.